We're all set?
Yeah.
Okay, welcome everybody to this week's department seminar. As always, just a quick few ground rules. If you're not speaking, please mute your microphone. And then whenever we go to the Q&A, you'll have the option of either raising your hand to ask a question, or you can type it into the chat, and then I will read it to the to our speaker today. So whichever one you feel better with. Let's see here. Trying to think of any department announcements. I don't think there are. We're on. I think this is the last one, right? So this is our last seminar of the semester. So this is the, I guess this is the headline act for the seminar for this semester. So the title of today's presentation, as you can see on the screen, is Recent Progress on Advanced Reactor Thermal Hydraulics. And it's being given by Dr. Rodolfo Vaghetto from Texas A&M University. Dr. Vaghetto is a research assistant professor at the Department of Nuclear Engineering at Texas A&M. He is a member of the Thermal Hydraulic Research Laboratory, where he is leading the experimental and computational research to accelerate the development and deployment of advanced reactor technologies, including liquid metal fast reactors, high temperature gas cooled reactors, and molten salt reactors. Dr. Vaghetto received his PhD in nuclear engineering from Texas A&M University, where he scaled, designed, constructed, and operated a natural circulation experimental facility to evaluate the performance of passive systems for advanced reactors. In 2015, Dr. Vaghetto established a multi-institutional project sponsored by the Department of Energy to design, construct, and operate a large replica of a liquid metal fast reactor wire-wrapped fuel assembly that has produced unique sets of high-fidelity experimental data of pressure and flow fields, used nationwide and worldwide for benchmark exercises and to support the improvements of predicting capabilities of specialized correlations. With the operation of this facility, Dr. Vaghetto has explored and developed innovative methods and measurement techniques for local pressure distributions and flow fields under a wide range of operating conditions. Dr. Vaghetto was part of a challenge project that led to the resolution of one of the most complex generic safety issues for light water reactors in history, the GSI 191, resulting to an innovative methodology that has been accepted by the regulator and referenced by several utilities nationwide. And with that, I hand the floor over to Dr. Vaghetto, and thank you for being here, sir.
Yes, thank you so much. And I really thank everyone for inviting me to speak today at your last department seminar of the semester. And I thank everyone joining the seminar today for staying with me for the next hour. I am particularly happy to present today, and the reason is because the Thermohydraulic Research Laboratory, where I work and conduct research, is strongly connected with several of the professors and researchers at your department. And approximately 1 year ago, we have established a new project that is led by Professor Avramova and Dr. David Holler, and that involves the use of some of the experimental data sets that we have produced from the 61-pin wire-wrapped fuel bundle replica, which is actually the core of the discussion today. So before I go through my presentation, I wanted to give you, I prepared a very quick overview of the current reactor technologies that are available in the United States. Okay. So this is an overview of the majority of the nuclear reactor design and technology currently under consideration. I divided by reactor technology, and if we start from the top, I selected some reactor vendors that are currently considering to reuse some of the technology available, especially the one coming from the large light water reactor currently in operation. And by doing that, they have somehow overcome some of the challenges that are related to the use of brand new technology of coolant. Still, there are some challenges here because the design, operating conditions, certain geometrical parameters are different and requires special attention and additional research and development. If we move clockwise on this slide, we go toward the technologies and coolants that have been less and less explored. So gas-cooled reactor, to be honest, have been around for quite a bit. There have been gas-cooled reactor in operation. There are new gas-cooled reactor went online recently in China. So the use of gas as coolant is not really a new idea. But the new ideas here that pose challenges to the core developers, to the reactor developers, is the different type of core designs. There are technology, they are using pebble bed designs, technologies they are considering graphite block, some other designs that they are still considering fuel rods in their core. So again, there is a very active research and development that needs to be accomplished before increasing the maturity level of this technology to be deployed for energy production. And if we move forward to liquid metal fast reactor, again, they are not relatively new, but not very old. And because of the challenges related to the use of liquid metal as coolant and the challenges related to the geometry of the core, have motivated a really wide range of experimental and computational activity worldwide. If we move to the molten salt reactor and the heat pipe microreactor, now we are moving toward technology that are relatively new, where experimental data are really relatively limited if compared to the ones available for light water, gas cooled and liquid metal. And here challenges are even more interesting, so to speak, and that's where the majority of the research and the development at the moment is focused. All these reactor designs, they share some challenges, and the challenges are related to the choice of the coolant type, the core design. I mentioned pebble bed, rod bundles or graphite blocks design. They are related to the choice of the neutron spectrum, rather than there is a thermal or fast reactor, and are finally related to their operating conditions. But so then why a reactor design may choose one option or another, or a combination of these options? Well, the reactor designers are currently working all toward the two main goals. One is safety, deploying a technology that provides the safest alternative and the safest source of electricity. And the second one is efficiency. So making sure that the operational costs are actually minimized so that that specific technology can be as competitive as any other clean energy sources available today. So our goal and our work that we are all doing as researchers is to make sure that we maintain a high level of safety and reduce the operational costs. Now, if I go back to this cartoon where I showed all the reactor technologies, I decided to select the liquid metal fast reactor that are actually in the middle. So there is a technology that is relatively mature compared to the molten salt and heat pipe reactors, but still requiring a very active research and development. Just to give an idea of the amount of activity and research that has been conducted worldwide, this map shows the location of the liquid metal research reactor that have been designed and operated in the world. And some of these reactors have a large size and are actually power reactor, like the one operating in Russia. And if I would overlap to this map, that research and development that universities like North Carolina State University, of Texas A&M University, or national and international laboratories, entities, and industry are currently performing in the area of liquid metal fast reactor. This map will be completely covered by small icon and pictures. So the reason why the liquid metal fast reactor are attiring with such attention is because there are certain specific design challenges, not only because they use a liquid metal as a coolant. Here I mentioned 3 of the current options that are considered, but because there are certain specific characteristics of the design, and I focus specifically on the core. Fuel rod bundles in liquid metal fast reactor, just because you don't need to use a moderator, they tend to have a more compact design. They change the lattice of the rod from a square lattice typical of light water reactor bundles to a triangular lattice. Now, by doing that, you have a more complex thermohydraulic behavior of the bundle because of the smaller sub-channel flow areas. But you have also other challenges. You have a higher core power densities. So here you need to really understand the phenomena involved in the heat transfer from the core to the coolant. In addition, there are several technologies currently under consideration for the spacers. So spacers in the fuel bundles are used to maintain the lattice during operation, so prevent the pin displacement. At the same time, reduce the flow-induced vibrations. Some spacer grid designs, for example, are meant to increase the heat transfer mechanisms, but every time you try to attempt to improve the heat transfer mechanism, normally there is a drawback, and the drawback is usually the pressure, and the pressure drop through the core, which is an important parameter when you design a reactor, not only for estimating the required pumping power, but also for safety reasons. I collected a selection of pictures of the current spacer technologies that are under consideration for liquid metal fast reactor fuel bundles. The one at the bottom is what is called the honeycomb grid. These 2 pictures are not actually taken from Google, but these pictures are pictures of spacer grids that we are currently investigated in our laboratory. And I have it here with me. If you have the camera on, you can see it. This is a typical spacer grid. It was 3D printed with the stainless steel 304. This is a typical spacer grid mounted in a 127 pin liquid metal fast reactor. And if you go to the picture at the top, it's another 3D printed spacer grid. This is used for gas-cooled fast reactor, while the coolant is different. As you can see, the geometry is very similar. And, and this was 3D printed with plastic material. Both spacer grid are mounted in dedicated fuel assembly replica that we are using to investigate the thermohydraulic behavior in this reactor core configurations. And there is also another interesting spacer technology that probably most of you are familiar with, and is the wire-wrapped spacer. So here, this technology consists of using a metal wire. The wire is actually wrapped individually on each pin. So there are no spacer grid at any axial location in the bundle, but there is instead a continuous spacer that is maintained by the use of this wire. So the wire is a spacer, so it has the same capability of a spacer grid. It maintains the lattice, it prevents a displacement of the pin during operation, and it also reduces the flow-induced vibration. But as you can see, the effect of the wire on the flow and heat transfer has an impact, and the behavior of the thermohydraulic behavior of these bundles are so complex that have motivated a very wide research, computational and experimental research worldwide. And that was basically motivated our laboratory, the Thermohydraulic Research Laboratory, to build the test section that I'm going to show you in a couple of minutes. But before moving that, I wanted to share with you specific challenges when studying the thermohydraulic behavior of these bundles. There is a very complex geometrical characteristic of the bundle. So triangular lattice, there is a number of pins that can vary based on the location of the fuel assembly in the core and based on the the core design needs. Usually these pins are enclosed in an hexagonal duct. So between the outer ring of the pin and the duct, you have a gap that is usually indicated with the letter W, and this is the edge pitch, and the P over D, the pitch over diameter ratio, which will give you an idea of how compact is the fuel bundle. And of course, the helical pitch over diameter ratio, which may vary and will tell you how fine the helical, the wire is wrapped around the pin. Of course, during normal operation, these bundles are supposed to work in the fully turbulent regime. But of course, during transient scenario, during accident scenario, you may transition to transition and laminar regimes. So if you combine together all these possibilities, you realize that you really need to have a wide variety of experimental data points that are important, not only because we have to understand better the thermohydraulic behavior and how each parameter and the combination of these parameters impacted the thermohydraulic behavior, but also because the experimental data are always important to validate the predicting capability of existing correlation, for example, the one for heat transfer or pressure drop, or I'm sorry, but I need to. But also because they are important to the validation of computational tools like system level code, sub-channel code, and computational fluid dynamic code. This is an overview of our test section. So the facility and the test section was designed and constructed under a project that a collaborative project with TerraPower, Arriva Framatome, and Argonne National Laboratory. So the test section is a 61-pin wire wrap replica. It is made of acrylic. It's a fully transparent, and the reason why we decided to fabricate this test section in acrylic is because we have employed high fidelity flow visualization and measurements that I will discuss toward the end of this presentation. The test section is also equipped with pressure measurements. As you can see here on the left, there are a series of pressure tabs that are installed at different axial location and different azimuthal location to characterize the pressure behavior for the bundle. The test section is connected to a forced convection loop. Here, we have installed a primary coolant pump. The pump is basically used to establish the desired flow condition at the test section, just to make sure the type of test we can conduct with our test section are what we call the isothermal tests. So we can conduct a test to study the hydraulic behavior, so the flow behavior within the bundle, we do not consider the heat transfer mechanisms, but still these experiments are important for the reasons I mentioned earlier. There is still an heat transfer system here. As you can see, there is a secondary system that you use to maintain the temperature of the primary loop under control. This is important because the fluid we use has a specific optical properties that change with the temperature. So it is important for maintaining the property of the fluid inaltered to maintain the temperature constant during the tests. And this secondary system is also used for filtration. We have a system level measurement of the flow rate. And as I will show you later on in the presentation, we have also camera and a laser that are installed to conduct the flow visualizations. This is an overview of the test facility with all the components that I just mentioned, so I will not talk more about the test facility. If you guys have any questions, you can ask me at the end if you are curious to know more about the test loop and the design of the test section. These are the geometrical feature of the bundle are basically have been provided by TerraPower. So TerraPower provided the test specification. We went through a series of iteration because since the bundle was built in acrylic, we had to face a certain engineering consideration, but these are the final dimensions of our test section. Of particular importance is what I mentioned before, the edge pitch. This edge pitch for this bundle is relatively larger compared to any other existing experimental test bundle of similar geometry. And it's because the vendor wanted to explore the ability to increase the edge pitch to further increase the lifetime of the bundle. During operation, this bundle may undergo thermal expansion and deformation of the pins and the duct. So having a larger edge pitch will allow to this thermal expansion, especially toward the center of the core. But again, you cannot work with a very large edge pitch, otherwise you have to face a large amount of flow diverted toward the periphery of the bundle. So as I mentioned before, the combination of all these parameters and the variability of the parameter like P over D, H over D, W over D, the pin number, the flow regimes, these are the main reason why we have found this motivation to perform additional experimental tests. And there are different correlations available, for example, to predict the pressure drop and the friction factor in this type of bundles. I think you are familiar with the Cheng and Todrea's correlation. This is one of the most used because one of the most validated correlations available for designers to use. And these correlations are probably the one that are the large amount of experimental data will go to for the validation or for improvement of the prediction. But recently also CFD computational tools have used this experimental data for validation of the capability of these CFD models. Now, the Cheng and Todreas recently have done a very extensive literature review to identify the number of experimental test bundles currently available and the number of experimental data points that they could use to further improve their correlation predictions. And they have identified 164 experimental test bundles around the world, including the one at Texas A&M University, with hundreds of data points in the laminar, transition, and turbulent regime. But for the reason that you can see at the top of the slide, these data points may appear to be a lot, but in the reality, we really need experimental data. As you can see here, for example, the laminar regime has not been really explored because historically researchers have focused more on the turbulent regime and then transition, but laminar regime is of interest, and developers of correlation like Cheng and Todreas have found data points in the laminar regime useful for improving the predicting capability of their correlation. So by reading the pressure drop over a one wire pitch on the side of our test duct, and we measure the pressure drop as a function of the flow rate. Then we normalize the pressure drop with the bundle average kinetic energy. And we plot in a log-log scale the bundle average friction factor with the bundle average Reynolds number. And you see all the experimental data set that we produced a few years ago compared with the prediction of selected correlations. And as you can see here, one of the things that we have noticed is that the Cheng and Todreas correlation is a correlation proposed in the middle 80s, have a good agreement with the trend of the experiments for our test bundle basically in a wide range of Reynolds number investigated. There are a few other information that you can get from this experimental data. For example, by intensify the experimental data set around the region where you are expecting the transition between regimes, then you can actually identify as close as possible the Reynolds number at which our specific bundle is transitioning from laminar to transition or from transition to turbulent regimes. And these are predictions that the correlation are able to provide. So this information is another information that is important for validating the correlation performance. One step forward in our experimental process was to go a little bit more in detail, and instead of analyzing the bundle average friction factor, we try to be a little bit more creative and to fill the experimental data needs, specifically in the interior subchannel regions. As you can see in the left side, the subchannels are not all the same. As a matter of fact, Cheng and Todreas have identified the 3 types of subchannel: the interior subchannel, the one that here are identified with the red, blue, and green colors, the edge subchannel, the one near the wall in orange, and the corner subchannel. And their prediction of the bundle average friction factor, it's a weighted sum of the local friction factor for interior, edge, and corner subchannel. So now if you think about all the large number of experimental data that I mentioned earlier, those are experimental data for bundle average friction factor. But if you count the number of experimental data for interior subchannel for local friction factor, then we want to say that the experimental data we have produced are really unique. So we have done some minor modification. The first thing is we replaced the acrylic duct with an aluminum duct, and this has allowed us to create additional pressure taps at the corner and at the edge. Then we designed and machined in our lab these rodlets that allowed us to measure the pressure at different azimuthal locations, as you can see here in this map on the left. And so we measured the pressure drop, we normalize it again, and we plotted as a function of the local Reynolds number, and we were able to show the local friction factor for 3 different subchannels: location 1, location 2, and location 3. And here, what we have noticed is that there are no statistically significant differences between the friction factor among the interior subchannel when moving from the center toward the periphery. But then there is also the prediction and the friction factor, experimental results for the friction factor for the exterior or edge subchannel and for the corner subchannel. In all the plots that I showed, there are two continuous lines, one of the same color of the experimental data, for example, in this case for the corner friction factor. And these are the prediction of the corner friction factor of the Cheng and Todras correlation, specifically the UCTD, which is an updated version of the correlation that was proposed by Cheng and Todras in 2018. And then there is the black line, that is the bundle average friction factor that will tell you what is the weight for each friction factor, for each subchannel toward the bundle average friction factor. So this basically is one of the most complex experimental activity we have conducted, only analyzing the bundle friction factor. We moved forward, and now I think I mentioned earlier, we were able to install the different pressure tabs at different azimuthal locations. So with the bundle of this geometry, with the wire rotating as you move upstream, as you move with the flow, you will certainly realize that the distribution of the pressure across one specific cross section may be of interest to analyze and understand. And the reason is because azimuthal pressure is important to know for estimation of the forces acting on the pins. Subsequently, you can estimate the pin displacement, or are important, of course, for flow-induced vibrations. So what we did is we installed a series of pressure tabs at different, in the midpoint of four faces, the one identified with the letter A, F, E, and D, at two axial locations. One is identified with PT5. It's in the full development region of the bundle, and it's in a location where you have the wire that is pointing toward the corner of these two faces, A and F. And then we have another location, which is PT6, which is 3/4 pitch downstream PT5, and where you see the wire is facing orthogonal phase E. So we measured the pressure difference across each adjacent phase, and then we found the different ways to plot the experimental results. And depending on how you plot the experimental results, we basically learned different information on the flow behavior in this type of fuel assemblies. One important takeover, for example, that we did by plotting the normalized pressure azimuthal pressure difference as a function of the angle of the wire compared to the corner between the two adjacent faces, is that there is a maximum pressure difference between the faces when the wire is actually pointing at the corner, basically at theta equal to 0. We have also learned, and you cannot maybe see in this plot by plotting in different configuration, is that when you increase the Reynolds number, you have a larger cross flow, and the cross flow impacted the pressure distribution across the same plane. So the Reynolds number that is normal to affect the bundle axial friction factor, in the reality will affect also the pressure distribution at each cross section. One of the last activity that basically kept us busy for about 2 or 3 years now is the estimation of the effect that localized blockages may have on the flow behavior. And here I'm talking about pressure drop again. Because the flow area of this subchannel is relatively smaller compared to a typical light water reactor design, these bundles are more prone to accumulation of debris in the subchannel. And when the debris accumulate, may create a localized blockage. Now, with the reactor core instrumentation, it's really very difficult to identify the presence of these localized blockages. But as you can imagine, a localized blockage may have a very strong effect on the heat transfer, and subsequently you can have a failure of a pin that basically can go undetected. So we used a systematic approach here because you need to know that these blockages may not have a very regular shape, and even the accumulation of debris may result in a blockage that is not a full blockage of the subchannel. It may have also a certain level of porosity. But if we wanted to study the effect of the blockage, and specifically how the flow area blocked affected the pressure drop, and how the location of the blockage may play a different role in the bundle friction factor, then what we did is we created very regular blockages that we were able to characterize with the conventional methods like using caliber, but also with the digital methods. So we know the exact flow area we were going to block, and we created different configurations. We have actually explored the 6 different configurations of blockages, where the blockage has been located at different location in the bundle. And by measuring again the pressure drop across one pitch within which this blockage is inserted, then we were able to study the effect that this blockage has on the bundle average friction factor. There are developers of correlations that are of course, are interested in using this experimental data to include the terms in their correlation to account for the effect of blockages. And of course, these are experimental data that are unique and valuable if you consider the validation of a computational fluid dynamic codes. So here you can see all the cases analyzed, including what we call the case 0, which is the free bundle without blockage. And they are all compared with the prediction of the Chengen-Todras, which predicts the friction factor with no blockage. So from here, you can see the effect of these localized blockages on the bundle friction factor. So if you want to know more about the experimental activity we have conducted, these are the list of articles that we have published only for the experimental pressure campaign. We have authors paper that we have published for the high fidelity velocity measurements that I'm going to discuss in the next 2 slides. So for some of you that are not familiar with the flow visualization techniques that we have adopted, the bundle has been built in acrylic, and we are applying what is called the matched index of refraction MIR technique that consists of using a special fluid. It's called the pisamine that has the same index of refraction of acrylic. When you couple the liquid with a clear solid material with the same index of refraction, you have this clear feature of the bundle that allows you to visualize the flow not only near the wall of the duct, but also within interior subchannels. And with some corrections and with some other algorithms that are in place in our lab, we are able to reconstruct the 2-dimensional flow fields at different locations in the bundle. We combine this technique with what is called the particle image velocimetry. This technique consists on seeding the liquid with the small particles, having a laser sheet illuminating this particle, and basically measuring the flow field by looking at the motion of the particles that are faithfully following the flow in the bundle. And with these two techniques, we have basically produced a relatively large amount of experimental data of flow field. These are more CFD level experiments. In other words, these are experiments that can be used for validating the CFD. As a matter of fact, a selection of these experimental data are currently shared with the project I just mentioned, led by Dr. Avramova, that will be part of an international benchmark exercise where people from around the world, they use their own CFD methods and tools and use the experimental data to validate their computational capabilities. We have applied the PIV for 2D PIV, 2D flow measurements. We have also applied what is called the stereoscopic PIV that will give you the ability to measure the axial component of the velocity within a cross-section on the bundle. And again, we have used the same technique adopted for measuring the pressure drop by installing localized blockages, but now showing how the flow structure is impacted upstream and downstream the blockage by the blockage itself. This is the very last slide of the presentation. In the next few minutes, I want to spend just a few minutes to give you an overview of the capability of the Thermohydraulic Research Laboratory, because we do a lot of research, and not only for this specific wire-wrapped fuel assembly, that anyway is one of the most active experimental and computational activity that we are conducting right now. We have approximately 30 between graduate and undergraduate students currently enrolled in our laboratory. We have partners, and we work with the Department of Energy, Department of Defense. We have a strong collaboration with the industry. We are fortunate to collaborate with national and international laboratory and university. And some of the experimental activity and experimental results we decided to share with the international benchmark, including the one that I just mentioned right now with Professor Avramova. We have developed techniques for measurement and simulations, and we currently support the research and development in pretty much all the reactor technology that I mentioned in my slide number 1. And we have in recent years expanded our research and development interest toward non-nuclear applications. We have supported the light water reactor industry. We have 3 light water reactor test bundles here in the lab, 2 that have been used for flow visualization and high fidelity measurements, and the one on the far right, there is a test facility that can operate at relatively high pressure and temperature for critical heat flux measurement. We have done single and two-phase flow measurement. And of course, we are engaged not only in the experimental part, but also we do a lot of computational work with system level and CFD level codes. We are we have installed a few weeks ago the NuScale small modular reactor simulator. This is one of the simulator that the NuScale have been installed, and it's actually an amazing tool. It allows students to run any accident scenario. That are predefined accident scenario can be executed, but we have the ability to access basically every component of the power plant, so we can basically create any type of transient. We have access to the plant operating procedures, so students are able to shut down the reactor, do refueling, start up the reactor from cold shutdown, change the power, and do many other operations, and it's all digital. The simulator represents a power plant with 12 units, and you can operate all the 12 units at the same time. We have also supported the development and research and development for high temperature gas cooled reactor. We have test and simulation for pebble bed and graphite block gas cooled reactor. We have also recently started an activity for rod bundle gas cooled reactors. And the picture that you see in the movie on the left is one of the most used passive safety systems that was designed for gas cooled reactors, but there are now in more and more adopted for other reactor designs, including molten salt, for example. This is the reactor cavity cooling system. And if you guys know David Holler, Dr. Holler was a student here, and his PhD was basically conducted using this experimental facility. And we are currently working on molten salt reactors technology as well. We have started this experimental activity approximately 2 years ago. We have built 2 forced convection test loop, as you can see on the left side. We have employed techniques for measured flow rates, pressure, and temperature that in high temperature corrosive environment are very challenging. And we have also conducted flow visualization using PIV in molten salt. Some of the molten salt, like FLINAC, are transparent at high temperature. And as I mentioned, as I discussed mostly during the presentation, we are also working on fast reactor technology. We have 3 fast reactor bundles here. The one from TerraPower that I discussed during this presentation, we just built a bundle for Westinghouse Electric Company for their lead-cooled fast reactor design, and this is 127 pin bundle. And then we have a bundle for the GA gas-cooled reactor. It's an 87 pin plus a central rod, and this is already in operation. We have done some experiment and simulation also for the upper plenum mixing, which is one important phenomenon for fast reactors. And this is my last slide. If you have, if you want to know more about the activity, or if you want to know more about the wire-wrapped fuel assembly, you can go to the website of the Thermohydraulic Research Laboratory. And with this, I will conclude my presentation, and you will be very welcome to ask any question you have.
Thank you very much for your presentation. It's wonderful. Okay, so at this time, I'd like to open the floor up for any questions anyone may have. Either please raise your hand in the, and I can call on you from the participant list, or if you prefer, go ahead and post something in the chat, and I can read it to our speaker. While we're waiting for people, I was kind of, I mean, how much? So I'm not a reactor core guy, but I mean, how much torque do you get on those fuel assemblies? I got to imagine those things are like a big propeller when you're spinning fluid through there, especially something like a liquid metal. Is that an issue?
You need to, like, the force that the flow itself apply to the bundle when you move upward.
Yeah, I mean, if they weren't bolted on the if they weren't bolted on the spacer, would they just spin?
Oh well, so yeah, what you see here, of course, the spacers are usually meant just to provide space, but the axial location of the bundle it's meant by some upper and lower nozzles. So the bundle is itself connected to an upper and lower plenum. So there is no way that it can move axial. So yeah, you have a relatively large forces depending on the type of spacing technology, but this is not in principle an issue because there are other attachments at the bottom and top of the core that prevented the fuel assembly from moving.
Right, but the wire wrap doesn't put a azimuthal torque on it. It starts to, I mean, imagine it's twisting those things or something.
Well, and that's, for example, if you look at the pressure distribution that I mentioned, that is very important. So the pressure forces that you develop by the fact that this wire will create like a transverse flow, it's actually important to know because it may create a pin displacement. It has an impact on the flow-induced vibration. So these are the reason why we are conducting this experiment. This is the major difference from, for example, of a light water reactor where you don't have these radial forces induced by the wire in this case.
Thank you. So we have one question on the chat from Chen Kai Tai, who asks, are there any special treatments to overcome the optical opaqueness of liquid metal so that PIV-like technique could be applied in liquid metal experiments?
Well, that is a good question. As a matter of fact, I would say if you in the future know of any way to apply a PIV technique in liquid metal, I will be more than happy to know. But you cannot apply flow visualization technique in the strict term of the definition, because again, by definition, you need to have a transparent fluid. And in fact, that's why all these tests that we have conducted with surrogate fluid. So now if you use a surrogate fluid, you can match a certain property and with proper scaling. Now, if you do hydraulic tests, so isothermal tests, like I mentioned, you care about the Reynolds number. So as long as you match the Reynolds number, all these techniques are available and the results you obtain are directly transferable to your final configuration, which is liquid metal. There are other techniques, if you mean PIV-like, you mean, for example, technique that will give you more high resolution measurements, then there are some technique for liquid metal like ultrasonic techniques. These are non-invasive technique that they may give you the ability to measure the flow in very small regions. So there are some other technique that you can deploy in liquid metal. In our experimental test campaign, we have chosen to use a surrogate. Subsequently, we were able to directly deploy the PIV in our bundle.
Thank you. Okay, any other questions from our audience? Last chance for the semester. After this, you got to wait till after Christmas to ask questions.
So what are the non-nuclear engineering applications that was mentioned that they are doing in their work?
Say that again?
Rodolfo, you mentioned that you also do some non-nuclear engineering application or measurements.
So non-nuclear applications?
Yeah.
So I believe I recognize the voice of Dr. Avramova, but I didn't actually hear the question.
So she was curious about some of the non-nuclear applications that you work on in your lab?
So molten salts, we are studying, molten salts are used for applications that are not as a coolant in the nuclear reactor. They are used as energy storage. So the same type of measurements that we have developed, we are trying to deploy in molten salt for energy storage. We have done a test for two-phase that are not directly related to the nuclear industry. So there are really a certain activity that we are trying to deploy for non-nuclear application. There are some space application we are also working right now, and where you can imagine all these techniques are available and can be easily deployed for non-nuclear applications.
So we have another question on the chat. Joy Fan asks, with MIR method in turbulence in a turbulent study, will the uncertainty increase in the thin boundary layer since the walls are not visible anymore?
Well, the measurement near the wall and very like within the boundary layer, so we are talking in the extreme vicinity of the wall, are very challenging, and everything depends on the light, the illumination, the calibration you are doing near the wall. So there is not a direct answer. In principle, the MIR method works, but it's the combination of your light source and the ability to see the particles near the wall without any other disturbance, and most likely is the reflection from the wall. That is what causes you to increase the uncertainty at the point that you really need not to consider your experimental data near the wall. And this is an answer that you will have depending on your geometry, depending on your setup, depending on your flow conditions as well.
Thank you. I mean, could you put this might be a silly question. Could you just, you still have the matched index of refraction, so you aren't getting the distortion of the laser light coming through the system, but could you use a fluid that has a dye in it so that even though you aren't getting distortion, you're still being able to differentiate between the wall location and the fluid? Would that help?
Yeah, that's basically, so even if you have a matched index of refraction, the matching is never perfect. And right. It's the ability of the experimentalist to quantify the uncertainty. So in the uncertainty quantification, there is a step, there is the calibration that allows you to estimate the distortion that you have for the presence of the walls, the solid walls, the liquid, the not perfect matching between the index of refraction and the walls. There is other type of research that you can do. For example, even further improve the matching between the liquid and the solid. So this is one thing that we have done in our lab. Instead of using, let's say, the coupling P-amine with the acrylic, we have explored other material and liquid that can give you even better and even more limited distortion when you run the experiment. So you have two ways to work here. One is quantify uncertainty. That is mandatory for any experiment. But second, try to minimize the distortion by using more sophisticated fluids and solids, clear materials.
I'm watching this time-lapse video, and I sometime not now, I'll be really curious to hear what kind of safety nightmare it is having that laser light reflecting off of everything while people are in the room. That's got to be that must have been fun. Oh yeah, well, in fact, this is a closed room, and everyone using the laser, you need to have the safety goggles on. The safety goggles, basically what they do is they screen the laser at that specific wavelength, and that is the way you prevent and you maintain safety when running these experiments. Still, it's impressive. I mean, I could just imagine our safety guy having a heart attack if he saw this. This is impressive. Oh yeah, yeah. Well, our safety guys, they have safety guy too, of course, and that's a major issue when you set up an experimental activity like this one, is making sure there is an area that is under control
You have safety feature to turn off the laser when someone accidentally opened the curtains or opened the door. There are sound and light alarms that are everywhere in the laboratory. And everyone, even the ones that are not allowed to use the laser, they need to take the laser safety training because they need to know how to cooperate with the experimental activity going on in the lab.
One more quick question, since they're not. What kind of laser is it? What kind of power is it? Is it just a YAG with a? It looks like a YAG with a.
Yeah, it's a green laser. The wavelength is 530 nanometer. The power, it's usually depend on the penetration that you need to achieve. We range from 10, 20 power laser. This is a pulse lasers, but we have also continuous lasers that we use for other applications. So, but most of our laser is in the range of 530 nanometer. We have other lasers that we use for other applications.
Great. Okay, well, if there's not any other questions, I guess we're going to go ahead and close out this session. Special thanks to our speaker for a great presentation. Appreciate it. Thank you. And thanks to everyone for participating.
Thank you for inviting, and thank you everyone for staying here.
Have a great holiday. Eat lots of turkey and see you in the new year.
Thank you, Rodolfo.
Thank you so much.